There's a machine out there right now, moving through absolute darkness, 20 billion kilometers from Earth, sending back signals that are taking over 18 hours just to reach us. It has no fuel left, no engine running, no human hand to guide it, and yet it keeps going. And what it is finding out there, in the cold, silent void beyond everything we have ever mapped, is beginning to rewrite what scientists thought they knew about the boundary that protects all life on Earth. Nobody's talking about this loudly enough, and that should terrify you. Let's be honest about something. When most people hear the name Voyager 2, they picture a relic, a dusty footnote from 1977, a spacecraft that belongs in a museum alongside bell-bottom jeans and 8-track tapes. They assume it is silent, finished. Only still alive, it is actively right now in August of 2026, transmitting data from a place no human-built machine has ever survived long enough to properly study. And just days ago, NASA completed one of the most audacious engineering operations in the history of space exploration to make sure it keeps talking. The question you need to be asking is not whether Voyager 2 is still relevant. The question is, what is it finding out there that is important enough to fight this hard to keep it alive? To understand why this matters, you need to understand where Voyager 2 actually is. Not in space in the general poetic sense, in the specific, almost incomprehensible sense. At a distance of approximately 11 billion miles from Earth, well beyond the orbit of Pluto, Voyager 2 entered interstellar space, the region between the stars. Think about what that means. It has crossed the edge of the sun's entire domain. It is no longer inside anything our sun controls. It is in the space between solar systems, drifting through a medium that existed long before our star was even born. And it got there under its own momentum from a launch that happened nearly half a century ago. No spacecraft in human history has survived long enough in that environment to send back real, live, instrument-measured data until now, and the data coming back is not what anyone expected. But here is where it gets interesting. Before we get to what Voyager 2 is finding, you need to understand what it crossed to get there, because that boundary is the thing that changes everything. Scientists call it the heliopause. The sun's heliosphere is like a ship sailing through interstellar space. Both the heliosphere and interstellar space are filled with plasma, a gas that has had its atoms stripped of their electrons. The plasma inside the heliosphere is hot and sparse, while the plasma in interstellar space is colder and denser. And in that interstellar space, there is something waiting that most people have never thought about: cosmic rays. High-energy particle radiation from exploding stars across the galaxy, constantly bombarding the edge of our solar system. Voyager 1 discovered that the heliosphere protects Earth and the other planets from more than 70% of that radiation. Read that again, 70%. The invisible bubble around our sun is the reason complex life can exist on this planet. And Voyager 2 is now on the other side of it, watching it from the outside, measuring it in real time. And what it is measuring is raising questions that no one can comfortably answer yet. When Voyager 2 actually crossed that boundary on November 5th, 2018, the instruments lit up with exactly the kind of readings scientists had theorized about for decades, but with one critical twist that nobody saw coming. The craft detected a sudden and extreme increase in cosmic rays. It also suddenly registered fewer of the charged particles that make up the heliosphere. And it saw a sudden jump in magnetic field intensity as it crossed over out of the heliosphere. These were expected. These were the textbook signals. But then the data started getting strange. The new papers confirmed that Voyager 2 is not yet in undisturbed interstellar space. Like its twin, Voyager 1, Voyager 2 appears to be in a perturbed transitional region just beyond the heliosphere. A perturbed region. That phrase, buried in scientific language, is extraordinary if you unpack it. Scientists expected clean interstellar space beyond the boundary. What they found instead was a turbulent, complex churning zone, a region that behaves by rules they had not fully written yet. The universe, it turns out, does not care about our theoretical models, and this is where everything changes. The data from Voyager 2's 5 working instruments began revealing details about this boundary layer that were genuinely unprecedented. Just beyond the heliopause, Voyager 2 discovered a boundary layer in which low-energy particles streamed outward along the magnetic field, and cosmic ray intensities were only 90% of those further out. This was not predicted. There was a zone, a kind of cosmic transition corridor, where the rules of both environments seemed to apply simultaneously. The interstellar medium was leaking inward. Solar particles were seeping outward. And the magnetic fields were doing something that made researchers reach for their instruments and double-check everything. An observation by Voyager 2's magnetic field instrument confirms a surprising result from Voyager 1. The magnetic field in the region just beyond the heliopause is parallel to the magnetic field inside the heliosphere. This was not supposed to happen. The model said the fields would point in completely different directions when you crossed from one environment to the other. Instead, they were aligned. That single data point forced a fundamental rethink about how the heliosphere is actually shaped and how it interacts with the galaxy around it. What most people are not seeing is that this is not just a curiosity for astrophysicists in conference rooms. This data directly relates to the long-term stability of the very shield protecting every living thing on Earth. According to informed sources within the scientific community, the heliosphere's shape and behavior is far more dynamic, far more responsive to external galactic forces than was previously understood. The instruments on the probe, still incredibly intact, started transmitting spikes in galactic cosmic ray strength and unusual changes in magnetic field strength, changes that shouldn't exist. The heliosphere was supposed to be a stable, predictable cocoon. The readings coming back from beyond its edge suggest something far more complex. A living, breathing, fluctuating boundary that responds to pressures from both sides. And if that boundary is more fragile than previously believed, the implications for planetary protection over geological timescales are not trivial. This is not an imminent crisis, but it is a discovery that fundamentally changes the framework through which scientists understand Earth's long-term cosmic environment. But the story does not stop at the boundary, because Voyager 2 has also been silently rewriting the history of our own solar system's planets during its long journey. In February of 2026, researchers published findings that reopened a 40-year-old mystery, one that had been sitting in Voyager 2's own archived data since 1986. Voyager 2's flyby of Uranus in 1986 recorded radiation levels so extreme they baffled scientists for nearly 40 years. New research suggests the spacecraft caught Uranus during a rare solar wind event that flooded the planet's radiation belts with extra energy. Similar storms have been seen near Earth, where they dramatically boost radiation levels. Think about that for a moment. A spacecraft that flew past Uranus 4 decades ago, data that was sitting in archives, and scientists only just now, in 2026, have found the key that explains what Voyager 2 actually witnessed during that flyby. The discovery is significant because it means everything we thought we knew about Uranus, its radiation environment, its magnetic structure, its behavior as a planet, was based on a snapshot taken during an extreme, once-in-a-generation weather event. And we were studying the exception and calling it the rule. And this is where it gets worse, because the implication of that discovery is that we may have fundamentally mischaracterized Uranus as a planet for 40 years. The discovery reshapes how scientists think about Uranus and why it deserves another visit. An entirely new mission would be required to see what Uranus actually looks like under normal conditions. We have been making theoretical models of the outer solar system based on corrupted baseline data, and the correction only came from going back and re-examining the work of a spacecraft that was never supposed to last this long. This is the real story of Voyager 2, not just what it is finding now, but what it is still revealing about the past. Now consider the machine itself, 48 years old, running on plutonium-powered generators that lose an estimated 4 watts of power every single year. Launched just a few weeks apart in 1977 for a groundbreaking exploration of the planets of the solar system, the Voyager spacecraft were originally expected to operate for only 5 years. 5 years. That was the plan. And here we are, approaching the spacecraft's 50th year of operation, still pulling critical scientific data from it. But that longevity has come at a cost. Every year, engineers have had to make brutal decisions about which instruments to keep alive and which to sacrifice. It is like a surgeon choosing which organs to preserve when a patient is slowly losing blood, except the patient is traveling at 55,000 kilometers per hour through interstellar space and cannot be operated on by any human hand. By 2026, the situation had become critical. Since 2024, the dwindling power supply has forced the mission to turn off 2 science instruments on each of the Voyager spacecraft. Each shutdown is permanent. Once an instrument goes dark, it does not come back on. The data it would have collected, the measurements of a region of space that no other probe will reach for decades, simply ceases to exist. It is not delayed. It is lost. Gone from the record of human knowledge forever. And by mid-2026, another instrument on Voyager 2 was scheduled to go dark before the year was out. The 3 remaining instruments, the magnetometer, the plasma wave subsystem, and the cosmic ray subsystem, were all at risk. Then, NASA's Jet Propulsion Laboratory did something extraordinary. Voyager 2's interstellar mission got a lifeline on August 4th, 2026, when NASA engineers completed the Big Bang, a simultaneous power component swap that kept all 3 remaining science instruments alive for at least 1 additional year. They called it the Big Bang. The name alone tells you everything about the risk involved. This was not a routine maintenance procedure. This was engineers working with software that was written before most of them were born, executing a simultaneous swap of multiple power components across a spacecraft 20 billion kilometers away, where every command takes 18 hours to arrive and another 18 hours to confirm. There is no room for error. There is no undo button. If something had gone wrong, Voyager 2 could have entered safe mode and gone silent forever. The procedure itself required a precise sequence of trade-offs. The Big Bang fix was implemented on July 9th, turning off 2 dedicated heaters and a digital tape recorder that was used solely for the residual heat it supplied. 2 different heaters and another device that supplies residual heat were switched on, but they draw less power than the devices that were previously working. In the brutal cold of interstellar space, where temperatures hover near absolute zero, approximately minus 273 degrees Celsius, heat is not a luxury. It is a survival requirement. The spacecraft's components must stay within operating temperature ranges, or they fail permanently. So every watt saved from power components must be carefully balanced against the thermal cost of losing that heat source. This is engineering at the absolute edge of human capability, maintaining a machine across 20 billion kilometers in an environment we have never physically visited, using technology 5 decades old to keep instruments running that have no replacement and no successor. Together, the 3 remaining instruments function as a continuous weather station at the outermost edge of the sun's influence, providing data that helps scientists understand how the heliosphere, the protective magnetic bubble the sun generates, shields the solar system from galactic cosmic radiation. Weather station. That framing is deceptively simple. What it actually means is that Voyager 2 is the only object in existence that can tell us, in real time, what the space around our solar system actually looks like from the inside out. No telescope can do what Voyager 2 does. A telescope observes from a distance. Voyager 2 is inside the data. It is immersed in the environment it is measuring. And right now, it is the only human instrument that has ever been there. The real story here, the thing that mainstream coverage consistently misses, is the irreplaceability of this data. There is no replacement for what the Voyagers are doing. No successor probe for interstellar space is currently funded, launched, or on a defined development path. Let that sit with you for a moment. The most distant scientific outpost humanity has ever deployed, our only eyes and ears in interstellar space, has no successor. No mission has been funded, designed, approved, or launched that will eventually take its place. When Voyager 2 finally goes silent, and that day is coming, humanity will go blind in that region of space. The measurements will stop. The continuous record will break, and the universe will keep doing whatever it is doing out there, beyond the heliosphere, without a single human instrument watching. Scientists at the Interstellar Mapping and Acceleration Probe mission, known as IMAP, which launched in 2025, are doing their best to complement the Voyager data from Earth's orbit. McComas describes its spacecraft, the Interstellar Mapping and Acceleration Probe, as IBEX on steroids, with the same basic capabilities, but at higher resolutions and taking additional measurements. But IMAP observes from inside the heliosphere. It maps the boundary from the inside, using energetic neutral atoms as proxies for what is happening at the edge. It is useful. It is important. But it is not the same as having instruments physically present beyond the heliopause. There is no substitute for being there. And right now, Voyager 2 is the only thing that is. The Voyagers are very much like biopsies of the heliosphere. We know nothing about the global 3-dimensional structure of the outer heliosphere from just these 2 sets of points. That quote, from a leading heliospheric scientist, is one of the most honest and humbling statements in modern space science. 2 data points, 2 trajectories through an incomprehensibly vast 3-dimensional structure. And from those 2 paths, taken by 2 machines, launched 16 days apart in 1977, we are trying to understand the entire shape and behavior of the sun's cosmic territory. It is like trying to understand the shape of an entire continent from 2 footpaths. The courage of that science, the willingness to work with incomplete data and keep refining the picture is extraordinary. And what does the picture show so far? It shows a heliosphere that is asymmetrical, that is shaped not just by the sun's output, but by the external pressure of the interstellar magnetic field pressing against it from outside. If the interstellar medium is becoming more unstable, or if solar wind of our sun is diminishing, it may be that one day our planet will be exposed to lethal cosmic rays in much larger quantities. This is not science fiction. This is the conclusion that researchers draw from the measurements Voyager 2 is sending home. The heliosphere fluctuates. It responds to solar cycles, to the sun's magnetic activity, to the density changes in the interstellar medium through which it is moving. And understanding those fluctuations on timescales of decades, centuries, and millennia is fundamental to understanding what makes a planetary system habitable over the long arc of time. Consider what Voyager 2 has already given us. It showed us that Io, one of Jupiter's moons, is covered in active volcanoes. the first time active volcanism had ever been seen on a world other than Earth. It showed us the complexity of Saturn's rings in detail that ground-based telescopes could never achieve. It gave us our only close-up views of Uranus and Neptune, planets that no other spacecraft has ever visited, and no funded mission currently plans to return to. And now, in its twilight years, it is giving us something even more profound: direct measurement of the space between the stars. Every data point it sends back is a piece of a puzzle that humanity may not have the tools to complete for another generation. The Big Bang procedure worked. The success of the procedure was reported by NASA in an update on August 4th, 2026. The technical team at NASA's Jet Propulsion Laboratory successfully carried out a power-saving procedure that has extended the working life of Voyager 2's spacecraft, which is running low on power from its generator. The 3 instruments are alive. The data is still flowing. For at least 1 more year, possibly 2, Voyager 2 will continue to send back its readings from the frontier, and engineers at JPL are already planning to perform the same swap on Voyager 1, which sits even farther from Earth, more than 25 billion kilometers away, in hopes of buying that mission more time as well. But this is where the story opens into something larger than engineering heroism or scientific discovery. It opens into a question about humanity itself. Here's a machine built with 1970s technology, running on power that is fading by 4 watts every year, carrying instruments that could go dark at any moment, transmitting signals across 20 billion kilometers of empty space. And it is still our best tool for understanding the cosmic environment in which we live. After nearly 5 decades of space exploration, after the International Space Station and the James Webb Space Telescope and the Mars rovers and the commercial space revolution, our deepest scientific outpost is still a device older than most people reading this. What does that say about where we have chosen to invest? What does it say about the questions we have chosen to prioritize? The universe beyond the heliosphere is not waiting for us to catch up. It is doing what it has always done, expanding, churning, sending cosmic rays and magnetic pressure and interstellar winds in every direction. And right now, one small machine the size of a compact car is our only ear pressed against that vast moving wall, listening for signals that might tell us something essential about the nature of the space we inhabit. Its power is fading. Its instruments are being saved one by one through acts of engineering that border on the miraculous. And somewhere out there, in the darkness between stars, it is still moving, still measuring, still sending. When Voyager 2 finally goes silent, and no one can say exactly when that will be, only that it will be, the data will stop, the record will go cold, and the question that will remain hanging unanswered in the silence is whether humanity will have learned enough from what it sent back to understand what we are truly surrounded by, whether the shield that protects us is stronger than we thought, or whether the readings coming back from the other side of the heliosphere are the early signals of something we are not yet equipped to fully comprehend. The probe keeps moving. The data keeps coming, and whatever is out there, whatever Voyager 2 is quietly measuring in the dark, it is not finished revealing itself yet.